discussion of polarizability. Just to recap, we talked about taking a neutral atom, exposing it to an electric field, E, and to first order, based on the multipolar expansion and all that, it would induce a small dipole, shift the nucleus a little bit that way, electron density a little bit the other way, creating a small dipole. We can expand this to things like Cu. Not in this order though. If we take this new molecule, which is roughly like that. In the center, we have the carbon, and on each side, we have the oxygen. Also, a neutral object, this molecule of Cu, but there would be some dipoles since the electrons are a bit more bound to the oxygens. Oxygens are a bit more greedy, but they balance out because it's in this nice linear thing. So there's still no dipole. If we applied an electric field, we'd get a little bit of a polarizability. But you can imagine that it's not going to be the same if we flip this thing. If instead we had the Cu oriented like this, carbon, oxygen, oxygen, that's going to respond differently. So their alpha is not actually going to just be the constant like we said before. This is where we'd have to use the IJ feature and say maybe it's easier to polarize it in this direction as compared to this direction. So you'd have this whole matrix of values, alpha in the x direction, alpha in the y direction, and so on, that would depend on the orientation of the molecule as compared to the electric field. Now for the next part, we're going to consider eels. No, just kidding. What we're going to consider is, instead of Cu, we're going to consider Mickey Mouse, right? What is Mickey Mouse? Mickey Mouse is a dipole. He's a permanent dipole built into the molecule, right? There's Mickey's oxygen, and he's got these two hydrogens up here. He has a dipole based on the charge. There's going to be negative charges pulled down towards the oxygen, these lone pair electrons and such. We're going to have this dipole shooting right through his head, pointing that way. So we can simplify Mickey into this object that has sort of a positive charge hanging out up here, negative charge down there, this little dumbbell-like thing, which would be kind of like an ideal dipole, just a very small distance separating a positive and a negative charge. So the question is, how does this interact with the electric field? Well, this permanent dipole that it possesses, that Mickey possesses, is going to be much more important than any of the induced dipoles the field will create. And it will tend to apply a torque to this thing to adjust its position. So we can write down what the torque would be. And for reasons that are perhaps not obvious, but we're just going to pretend that they are, the torque, which is this curly T thing called a tau, is just going to be equal to the permanent dipole P crossed with the electric field. And that makes sense if you consider angles and geometry, but that's the torque. Now, based on the torque, we want to know what is the work that the electric field will do. So for that, we'll need a picture. So to track down the work, let's consider this. We have our little dumbbell, the permanent dipole, oriented at some angle with respect to the electric field. What's this going to tend to do? It's going to pull on this guy that way, and it's going to pull on the negative charge that way, applying a force. It's going to create a torque, and this angle is going to be important. That's the angle between the orientation of the dipole, which is pointing up this way, and the electric field. So that angle theta, we'll use that. So we said previously the torque was P cross E, but we know we can just simplify cross products in terms of a magnitude of each of the vectors, sine of the angle between them. So that's the torque. We want to say, what is the work that the electric field would be applying to the dipole? What's the work going to be? Well, it's going to want to take this dipole and orient it so that it's parallel to the electric field. It's going to keep pulling on the positive charge, keep pulling on the negative until it's oriented right along the same axis. Just like that. There's the plus end, there's the minus end. So it's going to sweep out an angle just like that. So what we're going to do is we're going to integrate the torque to find the work. Integrate tau times d theta. And if we apply that integral, we know that effectively sine, when integrated, becomes a negative cosine. So the total work applied, the magnitudes are just going to pop out, is going to be minus p e cosine theta. Now that's another nifty formula. The magnitudes of two vectors times the cosine of the angle between them is just the dot product. So from that, the work that the electric field will do and related the potential energy stored if it's at a particular angle is just minus p dot producted with the electric field. And that's the equation. We've used it before, but just wanted to show it to you.